Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show modeling and safety analysis of fluid through a Venturimeter. This will be a very simple analysis. In this analysis, we'll try to find out the velocity and pressure distribution at two different points, and also throughout the central axis also to find out velocity and pressure distribution. Okay, so without wasting time, let us start modeling. We're starting from part. Let us select front plane. We have selected front plane. Next to that, we'll start with lines. Normally, we'll start with central line. Next to that, we want to create some lines without any dimension. Let us provide a specific line. Next to that, we can provide some dimension to this one. Start smart dimension. Let us have the diameter of this one to be 100 mm, so radius will be 50 mm. And let us consider this one to be 100 mm. Next to that, this angle should be actually 30 degree, so half of that angle will be 15 degree. This angle should be 15 degree. And again, this throat length should be 25 mm, and the height should be also 25 mm. This angle we have to consider as 5.5 degree. With smart dimension, let us make this angle to be 5.5 degrees. Great, check, done. The radius of this one should be 50 mm. So we can take from here itself the dimension. This one will be 50 mm. Let us make the total distance to be 550 mm. Done. Let us provide some thickness to this sketch, and that can be done using offset entities. We'll make outside direction by 5 mm. Green check, it is done. Let us make the sketch closed. It is done. Next to that, we have to rotate this one or revolve this one with respect to the central axis. So features, revolve boss base with respect to central axis. So it is done. Right? Okay, fine. Next one, what you have to do is, let us see from front view. We have to provide some manometric limb or manometric pipe. We have to provide one pipe in bent tube format. Right? For providing this one, let us start from front plane again. And we'll start with lines. Initially, we'll take some central lines. Again, another central line is needed to get the central location of this one. And at the throat location also, we have to have one central line to get the mid position of this throat location. Done. Now we have to start with normal lines, and let us make the line from this central axis. Later on, we can cut it as per our requirement. It is done. Now we can put some kind of fillet at the corner location. Let us make the fillet to be made up of 25 millimeter. It is done. Grain check. Next to that, we have to provide some features to make this one as a pipe. It will be hollow pipe, so we should go for swept boss base, and it should be having circular profile, and we want thin profile of thickness 1 millimeter and external diameter is 10 millimeter. This is made. We want to make this one in one direction only. Done. So this is a pipe which is having inside diameter as 8 millimeter and outside diameter 10 millimeter. Okay. For understanding this one, we can check it from left hand side. See, this is done, right? Now this is some unwanted portion. That one can be removed easily. So for removing that unwanted portion, we have to sketch one circle at the left hand side. So we can start sketching from here. Sketching is done. Now we have to use extrude cut. Features, extrude cut. You can cut it in the backward direction. So you can see from front view that we cut in the forward direction can provide a specific length. So it is cut definitely. Grain check. Now the same operation to be done for this throat location also. So for doing that one, we can do the same thing again. We can repeat the same thing. We have to draw one specific circle at this location. The circle of 25 millimeter radius is drawn. Grain check. Now you can see it from front view, and this circle to be extruded cut from this direction to the front direction. Features extrude cut, that we cut in this forward direction. You can provide the specific length of this one. It is cut perfectly. Done. Now you can see this thing from left hand side and check whether it is okay or not. So it is showing that it is perfect. And also another thing you can see from, you can have a segmented view of this model from front plane. Let us see the front view. Yeah, it is showing perfect. But the thing is, at this location, we have to provide some kind of holes. It is perfect, but at this entry and exit location, we have to provide some holes. So for seeing these things, initially what will make it, let us make the model to be completely transparent. Model is completely transparent. Now you can see the top view and make some holes at the entry and exit location of this manometric pipe. Select the top plane, and from top plane we have to draw those circular holes. Sketch. We have to select some certain lines to select the location of the centers. Again select center line. Same operation to be done for the same operation to be done at the throat location also. Done. Now we can start sketching circles at these two locations. Let us avoid any circle. Using relation, we can make it perfect. Now using relations, we want to make these two circles to be equal diameter. We select these two circles and make with equal diameter. These two circles are equal now. Now we have to put smart dimension to this one, as this one should be 8 millimeter. Done. Grain check. Now you can see from front view, and that to be cut. So this hole to be extrude cut in the downward direction. Features, extrude cut, and going to cut it up to specific depth. It's fine. Grain check. Now you can see this model from front view. You can cut it and see the segmented view of this model from front view. So it is showing perfect. Our model is ready for simulation, right? Next to that, we have to provide some kind of leads at the entry and exit location, because we want to have one closed volume for this CFD simulation or CFD analysis. Let's start from flow simulation, and from tools we can provide leads, create leads, exit lead is made. Now we can select the other side to make the lead at the entry location also. Two leads have been provided. Great check. The leads are ready. Now we can save this one with a specific name of Venturimeter. Then we can start our simulation. Let us save this one as Venturimeter. We save this one by the name of Venturimeter. The flow simulation environment will be initiated with the wizard itself. So let us select wizard, and we're keeping the name of the project as default project 1. Next to that, we have to select that unit system. It will be SI unit, and from pressure we can select pressure as bar, and temperature will be degrees Celsius. Though in this case temperature is not that much of important, we are considering temperature as degrees Celsius. Next to that, it will be an internal analysis, and from physical features we need to take only gravity, and the direction of gravity will be y. Along y it will be minus 9.81 meter per second square, and along z it will be 0. Next to that, we have to select liquid. We're considering default liquid as water. Next to that, default wall thermal conditions and roughness we are considering. And finally, we'll select the thermodynamic parameters. Pressure as 1.0132 bar, and temperature is 20 degrees centigrade. Let us finish this. So you can see this is the computational domain. Let us hide this domain. And one thing, so as a goal, we want to have XY plot through the central axis. We want to find out pressure and velocity distribution. So we need to draw something else. We want to have pressure distribution across the central axis. By the same time, we want to find pressure difference between the inlet and the throat location. So we have to draw something else. Let us go back to the model again and draw it. This is the model. We'll select the front plane, and let us start sketching at the front plane. Initially, we'll draw two specific points. As a point goal, we have to find out pressure and temperature distribution at these two locations. We have selected point number 1, and another point to be created at the throat location. 2 points we have created. Great check. We want to have another central line. With respect to the central line, we want to find out pressure and velocity distribution through this Venturimeter. It is done. Next one, we have to go back to the flow simulation environment again. Next, we have to select some boundary conditions. As through this Venturimeter, only one fluid will be moving, so we need not consider fluid subdomains. Only one fluid is there. We need not consider fluid subdomains. Now we have to apply boundary conditions, and always it is suggested to have a segmented view of this model for providing boundary conditions in a better way. So we'll cut the model along front plane and select the specific location for providing boundary conditions. Boundary conditions, insert boundary condition will be providing water from the inlet location at a specific velocity. Let us provide the inlet velocity to be 0.5 meter per second. Go and check. Another boundary condition to be applied at the exit location. Insert boundary condition. It will be atmospheric pressure at the exit location. Selected. Go and check. So two boundary conditions we have already applied. Next to that, we have to select some goals. Initially, we will select point goals to find pressure and velocity difference at the entry and at the throat location. Insert point goals. We have to find out total pressure and total velocity at the entry location. We can make this one visible from front view. Selected. This is total pressure and total velocity at point number 1. Again, you have to find out the same thing at point number 2. Goals. Insert point goal. We have to find out total pressure and velocity at point number 2. Selected. Go and check. Next to that, we have to find out mass flow rate or discharge at the exit location. That will be obtained through surface goals. Goals. Insert surface goals. We have to find out mass flow rate or discharge at the exit location. Go and check. It is done. Now when you select some equation goals, that means we have to find out pressure difference and velocity difference at the inlet and at the throat location. It will be equation goals, and the equation goals will be definitely obtained from the previous goals itself. So we have to add the goals. So we're going to find out pressure difference and velocity difference, right? So from continuity equation, we know that A1 V1 equal to ATV2. Let us see this from front plane. At this location, cross-sectional area is more, that is A1 is more, so velocity will be definitely less. And at this location, as cross-sectional area is less, so velocity will be more. So V2 will be more compared to V1. If you want to find out velocity difference, so second velocity will be more compared to the first velocity. Second velocity minus first velocity. Go and check. This is actually velocity difference between throat and the, we can rename this one as velocity difference. Next to that, we have to find out another goal, that is pressure difference in between throat and the inlet location. Goals. Insert equation goal. And again, we know that from continuous equation, as we told, Q equal to A1 V1. As at the entry location, velocity is very, very less. So pressure will be high at this location, right? So pressure difference we have to find out. It will be pressure at location 1 minus pressure at location 2. Grade check. Now we can rename this one as pressure difference. Done. Next to that, we have to run this and get our results. Let us run it. With new calculations, let us run it. Solver has already started iterations. You can view these results from the solver window itself. Let us see all the goals. It's clearly understood that the convergence criteria is achieved and we achieved all our goals. Right? We'll see the results from goal per second. Results. And first of all, we have to see velocity and pressure distribution across the front plane. Cut plots, insert cut plots. We need to see velocity distribution from front plane. Grid check. It's better to see these things in the form of animation, and let us make this line hidden. We'll see this velocity distribution through this Venturimeter in the form of animation. Let us play this. It's clearly visible that at the throat location, velocity is very high. It is in the range of 2.124 meter per second, and entry point it is 0.5 meter per second. Again, at the exit location also, velocity is very less. It is in the range of 0.4 to 0.9 meter per second. And also you can see through the manometric pipe, the velocity distribution also can be seen very clearly. It is in the range of 0 to 4 meter per second. It is very less. When you see pressure distribution from front plane. So it is showing pressure distribution at the bottom side. Pressure is very high, and next to that location of this throat, pressure is very less. It is in the range of 0.99 to 1 bar, and at the exit location we can see the mixed level of pressure is there. Below the Venturimeter part, we can see pressure is in the range of 1.02 bar, and as it is going up, it is 1.01 bar. It is better to see this pressure distribution in the form of animation. We'll see pressure distribution in the form of animation. Let us play it. And also you can see that pressure distribution through the manometric pipe, it is also having similar trend. Let us clear and hide these things, and we want to see dynamics of flow particles through this Venturimeter. Next to that, we want to see very important part, that is dynamics of flow particles through this Venturimeter. Insert flow trajectories, and we want to see these things in the form of lines and arrows. Initially, we want to see pressure distribution through this Venturimeter, right? Green check. The particle study is running. Let us play this. It is clearly understood that at the inlet location, pressure is very high. It is in the range of 1.02 to 1.03 bar, and at the exit location, pressure is little bit less, and near the throat location, pressure is very less. It is in the range of 1 bar. Let us view these flow trajectories in a different way. clear and hide. Let us see this thing in the form of spheres. Flow trajectories. Let us play. Let us clear and hide these things, and next to that we want to see XY plot. That means we want to see pressure distribution and velocity distribution across the central axis. For that, you have to go back to the model again and select that specific line along the central axis. Let us go back to flow simulation environment again. Now we want to see XY plots. That means we want to see pressure distribution and velocity distribution across the central axis. You can see other things like density of fluid also, pressure also we can see. Let us select the central line. We'll select pressure distribution and also velocity distribution across the central axis. And we can transfer this data to Excel. This is the data available. First one is velocity distribution across the central axis. Initially, the velocity is very less. It is in the range of 0.5 meter per second. As it is approaching towards the throat location, velocity is very high. At the throat location, velocity is in the range of 2.09 meter per second. And as it is approaching towards the exit location, again velocity is coming down. And finally, at the exit location, velocity is in the range of 0.86 meter per second. Next one is pressure distribution across the central axis. Initially at the inlet location, pressure was very high. It is in the range of 1.02 bar, and at the throat location, pressure is very less. It is in the range of 0.2 bar, and again as the flow is approaching towards the exit location, pressure value is increasing, and finally at the exit location, pressure is in the range of 1.01325 bar. Okay, let us close these things, and finally we want to see our goals from goal plots. Insert goal plots, and we want to see all our goals, what we decided before. All goals selected, that can be transferred to Excel. These are the summary of our goals obtained from Venturimeter. Let us see the pressure difference initially. This is the equation goal as the pressure difference. You can see after 16 numbers of iterations, pressure difference is very less. It is in the range of 0.2096 bar. Let us see velocity distribution or velocity difference. Initially, velocity difference was very high, and after 16 numbers of iterations, velocity difference between the inlet and the throat location, it is less. It is in the range of 1.02 meter per second. Let us see the mass flow rate or discharge at the exit location. After 16 numbers of iterations, mass flow rate at the exit location is 3.8 kg per second. The negative sign indicates that flow is going out of the exit surface. Okay, let us close this. So this is all about our today's analysis. Through this analysis, we have shown modeling and CFD analysis of fluid flow through a Venturimeter, and also we have shown pressure and velocity difference at two different entries, at the inlet and at the throat location. By the same time, we have shown velocity and pressure distribution through the central axis, and also finally we have shown the mass for it at the exit location. If you would like to understand CFD in a better way, you can follow my Udemy videos, link of which one is provided in the description box. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.